Okay. All right, so we have a quiz on Friday. We have a homework that'll be due on Friday at 7 a.m. Thank you. We have, I've got a help session on, well, tomorrow night, but Thursday at 7:30 p.m. 37. It's going to be 7:30 to 8:30 p.m. On Google Meet. Had about 5 people at that last time. Hopefully they found it really useful. Thought it was great having so many people at that. So the link to that is in your syllabus. My office hours are going to be Monday, or our Monday 1:15 to 3:15 p.m. and Friday 1:15 p.m. to 2:15 p.m. Okay, and then tomorrow have a number of people that have already talked to me about using time after about 11:30 for a couple hours. I'm going to be here, all right, automatically. But if you want some time in there, let me know. If you need time later in the afternoon, let me know. Okay, but I won't stick around otherwise. And the same sort of thing for this Google Meet. If it gets to be 7:40 and nobody's there, it's kind of rough on me to be doing these things on Thursday nights that late. I'm just going to leave. I'm going to go make dinner, something like that. Okay. So don't show up at 8 o'clock and assume that the thing is going if nobody's been there. Questions? Okay. So definitely seek out help. Actually, while we're talking about seeking out help, the Subject Tutoring Center sent me all these fancy double-sided printed things. You maybe have seen these before, but go ahead and pass those around. Take one. If you want to get help from tutors, that's a great way to get started there, and we have some really excellent general chemistry tutors. Okay. Questions? All right, then today we're going to be talking about vapor pressure. All right, so vapor pressure. Your book has a definition of vapor pressure that uses equilibrium and things like that. We are going to talk about what equilibrium is because it's an important concept, but I'd like to use a slightly different definition. This is going to be the pressure of a gas from a liquid above that liquid. So the pressure of a gas that is above a liquid that is caused by the molecules of that liquid. All right, so if I was to take this glass over here, I didn't do it last time. I don't know if the sink is on. I don't know if it's going to explode or something. Hold on. Nope. It's a nice water bottle. Whoever it was didn't leave it with water, though. All right, so if I've got some water in this beaker right now, and so this if I let this sit for a little bit, actually I'm going to have to put my hand over it to get some reasonable pressure. Otherwise, water vapor here, it'll just leave. Okay, but if I was to cover it, I will get a pressure in here based on molecules of water jumping out of the liquid. All right, and the actual vapor pressure, when we talk about naming it, we're usually talking about it after you've let it sit for a while and it's come to what we call equilibrium. Let's go ahead and talk about what equilibrium is. And we've got a nice little diagram below here. So I'll go ahead and I'll define equilibrium underneath it, or just above it. So equilibrium is the one on the right. Okay, but equilibrium, and we're going to use this concept in lots of places in this class. So I'm going to kind of give you a more general definition here. Equilibrium is the case where the production of, so here we could think about products being this and reactants being this maybe. Okay, I'm going to use products and reactants. is when the rate of making products is equal to the rate of making reactants. So that's what equilibrium is, okay? It is not equal numbers of products and equal numbers of reactants, or equal concentrations of products and equal concentrations of reactants. That is a common misconception. It is not when anything else is equal about the products and reactants. All right, for example, their concentrations. Does that make sense? All right, so when we look at our little beakers here, right? They've got a beaker, they've like my water here, they put a cap on to so stuff just didn't go away. And we start out, we're not at equilibrium here. We have molecules that will be coming up out of the liquid into the gas. And as we let it sit, some of the we'll have some molecules up here that are the gas. Those molecules that are the gas can bounce around up here, and occasionally they'll come back down into the liquid. And equilibrium, so here, but here we still have more molecules bouncing out of the liquid per unit time that come back into liquid. And then here at equilibrium, we have an equal number of molecules bouncing out of the liquid, becoming a gas as come back into liquid. Does that make sense? So at equilibrium, for every molecule that pops out of the liquid, one drops back down into the liquid. Does that concept make sense? Okay, that's what equilibrium is. And that's our vapor pressure. This is where we would measure our vapor pressure. Okay, and we talk about that. All right, so then we can think about vapor pressure is going to increase with temperature. Go ahead and put that right up the top here. All right, so as our temperature increases here, we have the vapor pressure over here. That's in millimeters of mercury. Okay, and as we increase the temperature for a number of solvents, let's go ahead and look at water. As the temperature goes up, the vapor pressure increases. All right, so the pressure of that gas above the liquid. Yes?
How come some of the molecules are coming out of the liquid?
How come some of the molecules are coming out of the liquid when we're not at our boiling point? Give me a minute.
Sorry.
No, that's great. That's an excellent question. I will get to it. Okay, so just wait a few minutes. So let's look at this though. So we've got our water here, right? We can read certain things off of this. What do you think? So they've got a special line that they have drawn here. They say normal atmospheric pressure, which is 760 millimeters of mercury. You probably don't know that. That's also 1 atmosphere. Easier number to remember. Okay, 1 atmosphere right there. If we look, what special thing happens when you reach atmospheric pressure? Oh, sorry, I can't draw. What special thing is going to happen? We're looking at water here, blue line. We're not at the critical point, but we're at a point. What would we call that point? The boiling point, right? When the pressure of the water bouncing out is equal to the pressure of the air pushing down on it, right? Atmospheric pressure, that's when boiling occurs. Let's go and write that one down. So when the pressure of, let's say the vapor pressure of the liquid is equal to the pressure of the air, the liquid boils. Okay, you could think about it, it's pushing just as hard up against the air as the air is pushing down against it. All right, this also explains some other things. So if we go up to a higher altitude, what did we say about water boiling? It doesn't take longer, we have to cook longer, right? Because water boils at a lower temperature, right? So let's say we go up to Mount Everest. I didn't look up, I should have looked up between classes what the pressure is at Everest. It's either 2/3 air pressure here or it's 1/3, and I can't ever remember. So we're going to call it half, right? I'm going to be wrong in both directions. But let's say this is our pressure at Mount Everest. So we're going to make it half of 1 atmosphere. Okay, 1/2 atmosphere right there. At what temperature does water boil on Mount Everest? I'm hearing 80, 80-ish, okay? Yeah, how do we do that? We followed this over to the water line, and then we followed that down, and we got about 80. Does that make sense, how we read one of these graphs? Okay? And this also tells you why water boils away at really low temperatures in outer space, right? Because in outer space, you've got a temperature right here, right? You got a pressure, really, really low pressures, so it doesn't take much in terms of temperature to get water to boil away. I think it probably sublimes. I think that was what we saw in the curves the other day when we were looking at triple points. Questions? Questions about this? How you would read one of these curves? Okay. All right. What's the boiling point of methanol then? That regular atmosphere pressure. About 60, right? Because what we're going to do is we're going to look at here's atmospheric pressure followed down. It's about 60. Okay. All right. So this gets to the question that you just had in terms of why do we get these water molecules? Why does water evaporate essentially, right? Because we know water evaporates. If I leave that water there, if we go look at that on Friday, I might have too much water for it to evaporate by then, but it might evaporate by then, right? Here, we'll pour a little of this out. All right, that's probably going to be evaporated by Friday. I'm not sure. But we'll see. We can watch it over time. It'll certainly evaporate in a few days. So why does that happen? Well, it turns out that all the molecules of a liquid have different energies, right? They don't all have the same energy at a given temperature. The temperature is a measure of their average energies. Okay, so at a given temperature, all the molecules of a liquid have different energies. Or we should say the molecules of a liquid, maybe not all, because some of them have the same energy. All right, so we've got different energies for these things. All right, the distribution of energies you get for molecules of a liquid is called a Boltzmann distribution. Okay, and there's an example of a Boltzmann distribution down here. All right, so you have kind of it's not a normal distribution where things are the same on each side. You end up with a bunch of molecules that have similar energies, and then you have this big long tail that heads off. All right, if I was to look at molecules of a gas, I would get the same distribution. If I was to look at molecules of a solid, right, Solids aren't moving around, but they still have energy. They'll have like a little bit of vibrational energy, and we would end up with something else as similar for a solid as well. Some of the molecules of the liquid will have enough energy to escape the liquid and turn into a gas. All right, so we can see that right here, right? We've got most of our molecules, or on average, or let's say the median energy is right here, maybe. Maybe it's a little over here, but in other words, we have an energy right here. This is our most populated energy, but there are some molecules of that liquid that have a lot of energy, and they have enough to jump out of solution at any temperature. Okay, and so that's why we get things evaporate, even though we are not at the boiling point. Yes.
How would the whole glass of water evaporate if some of the molecules are on the lower end?
That's a great question. So what's going to happen? How will we get some of these molecules evaporating, even though we're at that lower energy? You could imagine, let's say these have these high energies, right? And so they pop out of solution. So this liquid's sitting in air, right? These molecules on average are colder, but they're sitting in air, so they can still absorb more heat from the air. On average is what it looks like. So let's imagine it's not going to quite happen like this, but let's imagine they all jump out of solution at once. What you'd end up with is something that looks like, oh gosh, I can do better than that. What you'd end up with is something that looks something like this, right? Imagine just cutting off and they're all gone. And then it would absorb more heat from the air. These colder molecules would absorb some heat from the air, and then that would fill back in, and those would jump out, right? In reality, it's a continuous process. Some of these leave, and then it gets filled back in. Does that make sense? Until they're all gone. Okay, great question. Let's think about molecules, and let's go back and look at this, and let's think about what happens if a molecule obtains that energy. Does it immediately leave? So we're going to think about these molecules. What if I'm this molecule right here of water, and I'm right down at the bottom of that jar, and I get enough energy to leave? What's going to happen? Am I going to leave immediately? No, why not? Because there are water molecules in the way, right? So I can't. So you could imagine that this water molecule would wiggle its way out to the top and then pop out of solution, right? But it's not even that happens there, right? We've got it's a very dynamic process. Most of you probably played pool, right? If I take the pool and I'm going to do a break, I hit the cue ball super hard, right? Imagine the cue ball has enough energy to leave the table. I hit the cue ball super hard. It runs into the rack, right? Not the rack, but what do I call it? The rack balls. Whatever, the triangle balls. And if I hit it kind of really straight on, I can get the cue ball might stop. It would transfer all of its energy to the other balls, and all those other balls would start moving. So what's really going to happen is if this guy has enough energy to jump out, it's going to bump into other water molecules, and some of its energy is going to get transferred there. But that energy can get transferred up here, and eventually somebody near the surface is going to get enough energy to leave, right? And we talk about enough energy to leave, we're talking about enough energy to go from, put your hands up, right? Your hands are two water molecules. What happens when they leave? These two molecules, I have to break all those intermolecular interactions, and that water can jump out of solution. Okay? Does that make sense? All right. So that's kind of if you think about what the molecules are doing, that's the way to think about it. So we've got this Boltzmann distribution. We might talk a little bit might conceptually ask some questions about it. We're not going to do any calculations with it, but it's a very important distribution. Like I said, for anything at a temperature, you're going to end up with this sort of distribution of energies. Now let's do one more thing here. So let's pretend this is low temperature. Okay, that's a low temperature. If I was to go to a high temperature, what I would get is I would get a similar, I would get a Boltzmann distribution, but it would shift. It might look like this to my artistic ability, okay? So this is a high temperature. I probably have too many molecules over here, but if it's high enough temperature, it's fine. All right, and so at a high temperature, I end up with another Boltzmann distribution with a tail. Okay, probably a better, thinner tail than what I drew here. And then all these molecules still would have, these guys now all have the amount of energy to escape solution. And so what would happen at this higher temperature, would my water evaporate faster or slower? Faster, because a larger proportion of molecules have enough energy to leave the solution. Does that make sense? Okay. So we still get a Boltzmann distribution. It just pushes that bulge over to the right. Okay. Questions before I go on? Good questions so far. Thank you for everybody who's asking questions. All right, so we're going to now go on and we're going to talk about an equation called the Clausius-Clapeyron equation. I don't know that I actually spelled it last time, and I think it could be a disaster. I left my notes at home today, by the way. Clausius-Clapeyron. That's not right. I'm kind of afraid to go. I'm going to just say it's the Clausius-Clapeyron equation. You can look it up. Look up how to spell it in your book. I'm going to not go off of this because sometimes that causes my video to stop. But this is the equation right here. Okay, I'm going to rewrite it up above so we can kind of identify what the pieces of it are. And then we're going to play some games and modify it. So our equation is then the pressure is equal to some constant beta times E. This is the number E, 2.71 from math. Times the heat of vaporization, or to the raised to the heat of vaporization over ideal gas constant times the temperature. So let's go ahead and label those things in. This is the pressure in torr. Okay, this is a constant. That is different for every substance. Okay, this is our heat of vaporization or enthalpy of vaporization. So enthalpy of vaporization, what is that again? Yeah, it's the energy required to go from a liquid to a gas, right? So we've got our two molecules like this. If I had a mole of them, usually we're going to do this in molar quantities. If I had a mole of molecules stuck together like this, that's how much heat I would have to put in to make them come apart from each other, to break all those intermolecular interactions. Yes?
What is the top of that fraction?
The top of,
in the equation?
yes, delta H VAP.
Okay.
Okay? And no worries, you should ask that stuff. I am, so if you look down here, I'm just rewriting this. I don't know if you can see this one. Okay, fair enough.
Sorry, that's why I asked.
Do ask if you can't read my writing. So this here is the ideal gas constant. And that's we're gonna use the one that's 8.314 joules per mole degree Kelvin. There are lots of different versions of the ideal gas constant. They are the same constant, the units just change, okay? It's not that we have different ideal gas constants. And then the temperature over here, that's temperature in Kelvin. Okay, yes. 8.314, yes. And in this class, I will give you all the constants and I will give you all the equations. If you haven't had the class with me before, which most of you haven't, I'm going to go ahead and pass this around. This is like an equation sheet I would give you. All right, so I give you an equation sheet that has a mess of equations on it, even though we've only have, excuse me, you maybe have 4 so far in this class. But I'm just going to give you a mess of equations, and the ones you need are going to be on there. If you think I've forgotten an equation, you should always ask. All right, I might tell you, yeah, it's on there, or I might tell you, oops, forgot. Let me write it up on the board. Okay, so do ask. You'll be helping your other people out. And I'll also give you all the constants. So in terms of the ideal gas constant being 8.314, I'll give that to you. Now, I might give you all the other ideal gas constants as well. So this thing is coming around. The ideal gas constant has other units. The other one I've memorized is 0.0821 atmosphere liters per mole Kelvin. But there are more than that. So you need to know which one to use, but you don't need to know it from scratch. Okay, so we've got this great curve here then. So if I could plot the pressures versus the temperatures of a gas, and the vapor pressure versus the temperature of the gas, I could actually then solve for this heat of vaporization. I could solve for this, right? Those are constants. That's a constant, that's a constant. I could use a computer program to solve that, okay? However, I don't need to use a computer program, and classically what chemists have done is we like to make things into straight lines. And I can make this equation into a straight line equation by taking the natural logarithm of both sides. So we're going to talk about doing logarithms here. This is a good introduction. But let's look at this equation right here. It's a straight line up above when we plot the data, but if we look at it, it's also a straight line, right? The equation for a straight line is y is equal to mx plus b, y is my LNP, m is my heat of vaporization over r, x is 1 over t, and my b is my logarithm of beta. Does that make sense why that's a straight line? All right, so what I want to do though is you guys have not probably done a lot of stuff with logs. I want to show you how we get from here to here using logarithms. And we are using natural logarithm here, all right, which is more confusing than regular logs. First, let's go ahead and talk about what logs are. All right, so when we talk about logarithms, it's a way of compressing data that kind of has an exponential. If you have data that covers a really long range, you can use logs to get it all in the same graph in a way that makes sense. So in investing, sometimes they'll use this because you have compound interest. You guys may or may not know about that, or compounding of your investments. Other places you'll use it as well, but let's just talk about a regular log. So when I talk about LOG, okay, when we talk about LOG and we're not computer scientists, because computer scientists, this all goes wacky, and maybe mathematicians, it goes even more wackier. I haven't hung out with enough mathematicians to know. But when we talk about LOG, we're talking about log base 10, right? When we say log base 10, what we mean is our number system has its base 10, right? We count up to 10 and then we flip over the number, right? I go 1, 2, 3, 4, 5, 6, 7, 8, 9. Go to 10, I have to add another number. Then I roll up that 10, 20, 30, 40, 50, 60, right? 70, 90, 98, 99, 100, I have to add another number, right? Every 10 bases. All right, so I can take a log, we can talk about log base 10. If I have a number, the log of base 10 of 10 is equal to 1. Okay, the log, I'm just going to say log now, of 100 is equal to 2. Okay, the log of 1,000 is equal to 3. Does that make sense? Okay, and the way we can see that is in our base 10 system. I can put another log out here. The log 1,000 is 10 to the third, right? 10 times 10 times 10. 100 is 10 to the second. 10 times 10. 10 is 10 to the first. 10, right? Times nothing. Does that make sense how those logs work? All right. So then less obvious, or what less easy to think about, is this natural logarithm. This is the base e. So instead of 10 being our base for our system, 2.71, I think. Okay? Does that make sense? All right. So what we want to do is we're going to use these logs, and I'm going to show you how we get from the Clausius-Clapeyron equation, the form that doesn't have the natural logarithms in it. I'm going to get rid of the e, essentially. Okay? I'm going to put natural logarithms in it, and I'm going to get this straight line equation. And we're going to talk about log properties while we do this as well. So our Clausius-Clapeyron equation looks like this. Right? Okay. And so in algebra, I can do anything I want to one side of the equation as long as I do it to the other side of the equation. So what I'm going to do is I want to get rid of that e, and get rid of the e, I need to take the natural logarithm of it. Okay? So I'm going to take the natural logarithm of both sides. All right, so I've done that. Okay? I've taken the natural logarithm of both sides. It doesn't look very much better yet, but I can start dividing things up. So what I have here is I have the natural logarithm of b, right, times e to the raised to the negative h divided by RT. Okay? So what I can do is if I have two logs multiplied times each other, what can I do to break that up? Log property. You guys may not know this based on where you are in math, but so I'll teach you in here because we need to know this. I can break this up to be, if I have two things times each other, it's the logarithm of one times the logarithm of the other, or plus the logarithm of the other. Okay? And now what I have over here is I have the natural logarithm of e raised to something. Those go away. Okay, I'm not going to say they cancel. They go away. And a way of thinking that they go away is if I have 10 to the 2, right? I've got 10 raised to the power of 2. If I take the log of that, right, that becomes 2. The same way, so I'm taking this, the log base 10, right? Log base 10, the 10 and the log go away. All right? This is the log base e. So the e and the ln go away. Yes?
What is the E stand for?
The e is the number 2.17 something or other. Okay. Speaking of which, I'm going to pass these two calculators around so you guys get an idea of the type of calculator I want. What I'm going to do with it, with this one here, I'm going to put a 1 in. Let's see. There we go. 2.71828. I put e into one of them. But, so those are two examples of calculators that you could use for your quizzes. Remember, you have to have a non-programmable calculator. Okay, so the ln and the e go away in this case. So I can rewrite this now. I've got the logarithm of p is equal to the logarithm of beta plus minus the energy, the enthalpy of vaporization divided by RT. You guys with me for that? Okay, so now Remember, algebra, I do things to one side of the equation, I have to do the other. I can do anything I want, as long as I'm doing the same thing. Or doing things that are equal. So what I'm going to do is I'm going to swap the positions of these just so I can get this into the y is equal to mx plus b form, okay? And I'm going to do one operation as well. So I've got the logarithm, natural logarithm of p is equal to minus, right, plus minus is a minus, plus times minus is a minus, like that, plus logarithm of b, beta, I should say. Okay, guys with me? Okay, and then the final thing I'm going to do is I'm going to pull out this 1 over t. All right, so logarithm of p is equal to negative heat of vaporization over r. That's the heat of vaporization is a constant and r is a constant. The t is something I could vary, so I'm going to pull it out. But if I take that times 1 over t, it's the same as the thing I have up above. Times the logarithm of b, and now I've got what we had up above, which is an equation that is in the form of y is equal to m times x plus b. Okay, so it'll make a straight line. Does that make sense? All right, so what that means, we know, I'm going to wait and make sure everybody's done writing. It looks like you are. Yes? Nope? Okay. What I want to point out here, though, is we went from one to the other just using algebra, okay? Most of chemistry is you come up with something and you say, well, the world works like this. Obviously, this is what's going on. Or you have some base thing that you've accepted, okay? And then you just do algebra to it to get these equations that we're talking about. Now, the Clausius-Clapeyron equation, where we started, is kind of complicated and has an E in it, and it's not really one of these things that you just look at and say, oh yeah, of course it works like this, okay? But there are things in chemistry where you'll get to, of course it works like this, right? And it's something you can easily accept, or it's a base thing that somebody else has figured out you can accept, and then you can just do algebra and get the equations you want. Yes?
I know oftentimes, like in physics and stuff, you make it linear so that your slope is whatever it is that you're trying to find. Is
Yes.
that also what you're trying to do here? Or
Yes.
is it just to make it visually easier?
No, we're doing it because we're trying to be able to solve for things. Okay, so that's what's going on. Like what you said in physics, if we take this right here, right, that's our m. M is what on our line? Our slope, right? So this is our slope. And what is ln, the natural logarithm of beta, going to be on our line? It's our y-intercept, right? Questions on how we would use that if we had a plot? So, I was asking my wife last night whether I should have you guys graph by hand in here. And she said, oh, don't do that, you'll be really unhappy. So I'm not going to probably have you graph by hand in here. I haven't completely given it up, but I probably won't. But if I gave you one of these graphs already and I gave you the equation for the line, right, you should be able to solve for those things. Okay. And I might give you a homework problem or something where it says to graph, and you can use Excel for that if you want. They recommend you use Excel. Okay, so that's how we would do this. Now, what we can do, though, in here that isn't graphing is, notice if we have a really good straight line, let's say we have perfect data, do I need that whole line to get good answers? I don't. How many points do I need? 2 points make a line, right? And if all those points are perfectly on the line, it's not like real data. Okay, real data might be scattered a bit. If it's perfect in 2 points on the line, I could just solve it from 2 points. So how would we do that using this equation? Well, once again, we can use our friend algebra, right? So let's say I've got 2 points. All right, and so this equation for point 1, or for condition 1, we could talk about. These are constants. So I've got a pressure 1 that goes with a temperature 1, right? A vapor pressure 1 that goes with a temperature 1. and plus logarithm beta, right? Logarithm beta is also a constant, so it doesn't matter what the temperature is. All right, there's one condition. Then I've got another condition, 2. That's going to be my vapor pressure over my R, still a constant. 1 over, it's got a new temperature to go with the pressure, right? Temperature 2, plus the logarithm of beta. All right? Remember, I can do the same thing to each side of the equation, right? You do whatever I want to the equation as long as I do the same thing or equal things. This is equal to this, right? So I could subtract this from this side and this from this side. I'm doing the same thing to both sides of the equation. Does that make sense? Okay, so I'm going to do that. So that's going to give me a logarithm of P1 minus the logarithm of P2 is equal to minus H VAP over my ideal gas constant, T1. I'm going to go ahead and combine, do my HVAP turn next. So then I'm going to minus, right? HVAP over R times 1 over T2, right? I'm subtracting the lower equation. We're subtracting these two here. And then I'm going to write plus logarithm of beta minus, because we have the logarithm of beta. That makes sense what I just did? Okay. What happens to my logarithms of beta? They cancel because I've got a plus and a minus. Those are gone. All right. Now, if I want to clean this up, I can clean this up a little bit more. If I have the logarithm of something minus the logarithm of something else, how can I rewrite that? P1 over P2, right. So above, we split them up. Here, we're going to put them back together. Logarithm P1 over P2, like that. Okay, and then I can take this and I can distribute it, right? I've got something here and they're the same times something. So I can go and rewrite those. I'm not distributing, and I'm doing that. What is the opposite of distributing? Is it factoring? Okay, thank you. Delta HV VAP R, right? Times 1 over T1 minus 1 over T2. And there we go. That's the 2-point form of the Clausius-Clapeyron equation. Once again, we just did algebra together. Questions? Okay. Hold on to that. I'm going to give you a graph next. We'll do a graph problem and ask some questions or reading a graph problem, and then we're going to come back and use this equation. We'll use it to answer a question. So let's scoot down here. Based on the pressure temperature curves for ethyl alcohol and acetone, which are going to be shown below, let's answer these questions. First off, which liquid is most volatile? What does volatile mean? Unstable, or it's actually the one that's going to end up in the air the most. Okay, so volatile, we talk about volatile, end up in the air the most, or most likely to evaporate. Okay, so let's go ahead and answer these questions. See if I'm going to have to shrink this down. Okay, now we have everything on the screen at the same time. So based on this, don't answer the questions right now. Go ahead and write them down. Answer all 3 questions for these 2 liquids based on the graph. I'll give you a minute and then we'll talk about it. Yeah, you're welcome to discuss it with your neighbor or whatnot. It helps you understand it. Okay, let's go ahead and look at these. Which one's the most volatile? Which one will have the most vapor in the air at any given temperature? What was that? Acetone, right. It's going to be acetone. Which one has the highest vapor pressure at any temperature? It's kind of the same question. Also acetone, right? At any temperature, you go up here, acetone is the acetone line is above the ethyl alcohol line. So acetone. And then finally, which liquid has the highest boiling point? Ethyl alcohol. You put it at the most temperature. Where is the boiling point on this graph for each of these? Well, okay, so acetone, you're saying it's about, I'm going to say, okay, so let's do this. Right? I'm going to take this 1 atmosphere pressure, right? That's where we're talking about our boiling point. So that across, where does it intersect? Acetone has a boiling point of about 55, 6, 7. And ethyl alcohol has a boiling point of about, not 89 because we stop at 80, but 70, 78-ish. Okay, something like that. Okay, that's how we read those. So you should be able to look at one of these graphs and read back and forth. And you shouldn't be surprised, I don't know, I haven't written your quiz yet, but you shouldn't be surprised if you see something like that on the quiz. Okay, so now we've got a use for our 2-point Clausius-Clapeyron equation. Here's a good problem for that. So if we take this problem here, use the data below to find the heat of vaporization for butane. So I could plot these, right? I can get slopes off that plot. I could look at the y-intercept. I could actually do a 2-point plot, but I could also just use our 2-point Clausius-Clapeyron equation. So we have that the equation was the logarithm of P1 over P2 is equal to negative heat of vaporization over R1 over T1 minus 1 over T2. Right? That match what we had in your head earlier? I'm just doing it by memory here. So now what I've got is I'm given the pressures, I'm given the temperatures. I look at that sheet that I passed around to find my R, right? And I find out that R is equal to 8.314 joules per mole Kelvin. All right, and knowing that, I now have that, and that. I've got an equation, I've got everything except heat of vaporization, so I can solve for that. All right, I do need to be able to do the log thing on my calculator. So I'm going to go ahead and we'll write out what it looks like over here. The logarithm of, I'm going to take pressure 1, I'll call the top one pressure 1, and this will be pressure 2. So we're going to go 400 and, whoops. 458 over 686. I also forgot my glasses. It's really been a morning. Is equal to negative times the heat of vaporization of 8.314 joules per mole Kelvin times 1 over T1 is 260 minus 1 over 270 Kelvin. Okay. Note that the other class loved this. No, they didn't. They just stayed quiet. But the Kelvin here is on the bottom, right? We got the Kelvin is on the top of the bottom. Does that make sense? It's on the bottom, but it's on the top of the bottom. Whereas the Kelvin over here is on the bottom of the bottom. Do you see that? So I can cancel the kelvins. I'm going to get a minus Kelvin out. So this Kelvin, you see that since this Kelvin's on the bottom, I can flip them on the top, or whichever way you want to think of it, I can cancel the kelvins. Okay? They're on different levels. All right. I'm going to start putting these in my calculator though. So calculator is being passed around. Is that mine right there?
Yeah.
There.
Okay.
All right. So yeah, I recommend if you've got whatever calculator you've got, whether it's one I'm gonna be comfortable using or not, practice using it. And see if you get the same answer as me. All right, so this is one of those things where I can't kind of put it all in the calculator at once, or if I was more clever, maybe I'd think of a way to do it. But, okay, I got this over here by dividing the two and taking the logarithm. And then I'm going to write the rest of it out. And then I'm going to do the part in the parentheses. I'm so glad my calculator understands order of operations. It makes this easier once you're confident in your calculator. And I'm just taking everything out to 3 significant figures because what went in was 3 significant figures. I'm assuming this temperature are 3 significant figures, even though they're actually written as 2. Okay, and so now what I need to do to get heat of vaporization by itself is I'm going to need to multiply both sides by 8.314 joules per mole Kelvin. Oh wait, the kelvins are gone. And I need to do that over here. So it's joules per mole, which by the way is the units of a heat of vaporization. So I feel good about that. And then I'm also going to divide both sides by 0.000142, which has no units anymore because we canceled them. Okay? And so if I do that, those cancel, these cancel, and so then I'll have heat of vaporization by itself. And what I get is what I got last class. But so you guys can tell me whether I messed up on last class and this class. So I've got 230, I'm going to round it for sig fig, 000 joules per mole is equal to the heat of vaporization. So I have this negative, make sure you've got a negative there and negative there, so they're going to cancel as well. Is that what other people got? Okay, and if I really was doing my units, this would be fine in terms of units. Joules for heat of vaporization, what was that, butane? Okay. Questions? Okay, and if I wanted to do that in kilojoules, then you could do dimensional analysis to convert it, or it's 23.7 kilojoules per mole, which is the units that when we had the table before, they were recording these in. Yes.
Could you go over the buttons, how much work they do for us to get
The logarithm?
Yeah.
Absolutely, that's a great question. So let's talk about the buttons for the calculator. So you've got your calculator, right? Go ahead here, and so what I'm doing just to get from here to there, I put 458 in my calculator. I divided by 686. I pressed equals, okay? And then I've got an ln key on my calculator. I pressed the ln key, and that's what I got back. Does that work? Okay. You're not going to be able to use your phone. Definitely not going to be able to use your phone on a test for a quiz. Questions? Yeah. What is the what? This butane. Because the problem, I think the problem was about butane, if I remember. Yes.
Are the 8.314 over there, and that was just multiplying it, right? I know it's like kind of on top, but.
Yes. So I multiplied this side, so that just canceled, and I multiplied by that side. Yes. Okay. Anything else? All right, so I think what I'm going to do is pass your quizzes back. Most of you I did not have last term. So here's something where you might do this where you'd graph. Okay? But like I said, I'm probably not going to have you graph in here. So I'm going to go ahead.